Hello and welcome to another lecture associated to the project stories. The topic of this lecture focuses on the potential role of ammonia and other energy carriers for hydrogen storage and transport, challenges and opportunities. My name is Antonio Vita. I am a senior researcher at the National Consortium of Research of Italy. I work at the Institute of Advanced Technology for Energy Nicola Giordano in Messina. The National Research Council is the largest public research institution in Italy. The CNR has around 80,000 employees between researcher, technician, administrative, and 8 departments that cover different topics of human knowledge. From chemical science and material technology to social science and humanities, including earth system science, biology, agriculture, food, ICT, and biomedical science. Finally, the CNR is present throughout Italy with 88 institutes, each dealing with specific topics. The institute in which I work is part of the Department of Engineering, ICT and Technologies for Energy and Transportation. The headquarters is located in Messina City in Italy, together with a test center for prototype and technology transfer. Other secondary cities include the unit in the University of Palermo and the unit inside the electrical center of Augusta. The institute staff include about 128 people, between researcher, technician, administrative, and so on. Our institute is dedicated to advancing research and innovation in the energy sector. Its activities focus on the development and optimization of sustainable energy technologies, including hydrogen production, CO2 recycling, fuel cell, energy storage solution, and social and environmental impacts. Institute is active in many research projects in the framework of European, national, and regional research programs in the area of clean energy. Now let me give you some very little information on my research team. Our activities are developed within the framework of two main topics: chemical energy storage, carbon dioxide recycling, and hydrogen carrier, and hydrogen production from fossil fuels and renewable fuels like biogas, bioethanol, ammonia, and methanol. We are involved in the intensification of thermochemical processes in general, and we are also involved in several projects, European project, national project, and regional project, in which we develop catalysts, especially structured catalytic system like 3D printed catalysts. We developed also reactor and we scale up also catalysts, and finally we develop also prototype. I'm the head of this team, and do not hesitate to contact me for further information. Coming back to the lecture, before to go in deep in the topic of this lecture, I would like to give you some information on background of energy system. The energy system has transformed dramatically since the first and second industrial revolution. We can see this transformation of the global energy supply in this graphic shown here. It graphs global energy consumption from 8,000 onwards. The demand for energy is growing across many countries in the world as people get richer, and especially as population increase. If this increased demand is not offset by improvement in energy efficiency, then our global energy consumption will continue to grow year on year. A breakdown of global energy production by source show that today fossil fuels still account for the majority. Around 77%, more or less, of global energy comes from oil, coal, and natural gas. Despite the increasing of focus on cleaner sources, the contribution of renewable energy now accounting for around 20%. Instead, nuclear energy represents roughly 3% of the total. Graphic here is strictly connected with the previous one. In this chart, we see the growth of global emission from the mid 18th century through today, and we see that before the industrial revolution, emissions were very low, and a growth in emissions was still relatively slow until the mid 20th century. Then the emission have continued to grow very quickly, and we now emit over 35 billion tons each year. So we can say that human activity is responsible for the vast consumption of energy, primarily from fossil fuel, and leading to a significant pollution and environmental degradation which intensify climate change. It's widely recognized that to avoid the worst impact of climate change, the world needs to urgently reduce the emission. But how this responsibility is shared between regions, countries, and individuals has been an endless point of contention in many international discussion. The European Union aims to be climate neutral by 2050. With this sign, the European Union won't lead the way by investing in clean technology solutions. The windows to reach zero emission by 2050 is quickly closing, but there is still time for the world to get on track. If decisive action is taken now, if we want to reach net zero, we need to stop using fossil fuel and cut emission right way across the world globally energy system, including power, transport, industry, and buildings. There is no doubt that renewables are the future of power generation in Europe and worldwide. Reaching net zero depends on tripling renewables capacity by the end of this decade. We can say that the era of fossil fuels is ending on near to end. Even if the transition is driven by economic aspect alone, renewables could still generate 50% of electricity by the end of this decade. Continuing to move away from fossil fuels will also require investment in clean technologies to accelerate the adoption of renewable energy sources and the removal of carbon dioxide from the atmosphere for storage and use in industrial processes. Most renewable energy power generation is location dependent. Renewable electricity generation is sensitive to weather conditions and guaranteeing the amount of energy produced at any given time is a challenge. Intermittency highlights the need for energy storage solution. Batteries, for example, are required to collect energy during peak production period for distribution in a controlled, consistent manner during period of low or non-production. But also chemical storage way in molecules like hydrogen and hydrogen derivatives such as ammonia, methanol, and methane can play a key role to manage excess energy and use partly of carbon dioxide sequestered. Chemical storage can add power into the grid and store excess power from the grid for later use. We are talking about power to gas or power to liquid technologies. For instance, a way to stabilize the energy sector could be to use water electrolysis to produce hydrogen in periods with excess electricity production. Then the hydrogen could be used for application to decarbonize industry, transport, heating, and power generation. On the negative side, the major challenges for the use of for the direct use of hydrogen as an energy carrier is the low volumetric energy density. But hydrogen can be used in the synthesis of other storage molecules with higher volumetric hydrogen storage density and higher gravimetric hydrogen storage density, like, for example, ammonia and methanol that can be stored and transported for application in industry, transport, heating, and power generation sectors. As just said, the renewable power is intermittent and thus not always available when needed. Consequently, we need tremendous conversion and storage capacity in order to have a continuous energy supply. Direct electrification is the best option for energy conversion efficiency and zero tank-to-wheel emission, but the low energy density of battery electric storage systems make them unsuitable for large energy storage such as in the maritime sector. Considering the intrinsic properties of potential energy carrier reported in this slide, from boiling point and energy density perspective, methane, DME, methanol, and ammonia are the easiest to handle. And also the equivalent power density in the transportation of fuel is also strongly in favor of storage in terms of fuel for airplanes, ships, and trucks, and also to some extent for passenger cars. Direct use of hydrogen, either in compressed or liquefied form, has some advantage. One of them is the fact that it requires a less complicated fuel production process. But even in its liquid form, hydrogen has a relatively low energy density compared to other synthetic fuel. When we talk about energy carrier, we have to take in consideration different aspects. Methanol, for example, has high energy density even compared to ammonia and is generally simple to handle. But in this case, the final cost of the fuel and just the financial feasibility is heavily dependent on the cost of carbon dioxide supply. Liquid organic carriers, for example, come with these own unique challenges. It can be stored in standard maritime fuel tanks, but the spent carrier, once the hydrogen has been extracted, needs to be also stored on board. Ammonia is another interesting molecule for chemical energy storage. And ammonia as a maritime fuel offers a good balance between good energy density and relatively low fuel production costs that in this case is not influenced by carbon dioxide supply cost. The maritime sector offers a scenario in which these emerging carriers can be compared. Hydrogen, ammonia, and methanol, for example, have been proposed as promising energy carriers that would replace part of the liquefied natural gas in future maritime scenarios. Energy efficiency is an important indicator for evaluating each system. As reported in the figure, the emerging efficiency of the maritime supply chain of hydrogen, ammonia, methanol, and natural gas include ship sites, production, storage, energy loss of cargo handling system, loading, transport, unloading. Many aspects should be compared. If we look at the graphic on the right, we see that ammonia and methanol have much lower energy losses in the liquid supply chain than natural gas and also liquid hydrogen. And this means that it can be transported efficiently over long distance, especially. So in the future, ammonia and methanol could be used as an alternative energy carrier to transport renewable energy by sea from countries with higher renewable energy potential to countries with high energy demand, like Europe, for example. In the next slides, I'm going to give details on ammonia, on application, properties, synthesis, and production costs. Ammonia is a colorless gas with a distinctive pungent smell. On the right, you can see the most common properties of ammonia, but the most important for chemical hydrogen storage is the capacity of ammonia to store hydrogen through chemical bond. Ammonia has a very high hydrogen density, approximately 121 kilogram of hydrogen per cubic meter, in liquid form at minus 33 degree centigrade under atmospheric pressure. This value is higher if compared with other potential carriers like methanol or liquid hydrogen. And many experts suggest that using ammonia as a temporary vector for hydrogen will be needed to overcome the storage and transport challenges associated with hydrogen. Today, about 30% of the annually produced ammonia is used for fertilizer production. But ammonia is also used for textile industry, explosive industries, cosmetic industry. Ammonia production normally increase with the increase of population. And in the future, the ammonia production will increase much more, driven by economic and population growth. And this number will increase much more if we consider the application of ammonia in the energy sector as an energy carrier. China is the largest producer of ammonia, accounting for 27% of production. Then we have other countries like the United States, European Union, India, and Russia that produce about 10% of ammonia. One of the advantages to use ammonia as energy carrier is the well-established international existing infrastructure for ammonia transportation and storage. There is a comprehensive network of able around the world that can handle ammonia on a large scale. This well-established infrastructure can be used also to transport ammonia for energy application. The Haber-Bosch process is the primary method in producing ammonia from nitrogen and hydrogen. Fritz Haber and Karl Bosch, both Nobel Prize in chemistry, worked together more than 100 years ago to develop this important process. Fritz Haber was the first that demonstrated the process at lab scale, working with high temperature, 500 degrees centigrade, and high pressure, between 150 and 200 atmosphere. Karl Bosch demonstrated the feasibility of the process at large scale, for an industrial production. The first full-scale Haber-Bosch plant was erected in Opau, Germany, and this factory was able to produce 30 tons of ammonia per day with 300 kilograms of iron-based catalyst. Here we have the reactor fused. On the right, we have a simple scheme of the process, in which we have a principal reactor. Inside this reactor, the reaction occurs at that pressure and that temperature. Then we have a heat exchanger system to recover heat, and a condenser and a refrigerator system to recover ammonia in the liquid state. Then hydrogen and nitrogen not reacted go inside the heat exchanger to be heated, and then are sent to the reactor again to increase the productivity. The ammonia synthesis is a reversible reaction. It can proceed both in forward direction, ammonia synthesis, and in backward direction, ammonia decomposition. The reaction is characterized by decreasing volume. So, increasing the pressure causes the equilibrium to shift to the right, resulting in a higher ammonia production. Decreasing the temperature also causes the equilibrium position to move to the right again, resulting in a higher yield of ammonia, since the reaction is exothermic. The reaction does not proceed at ambient temperature, because nitrogen requires a lot of energy to dissociate. The use of catalysts, of course, accelerates the reaction. If we look on the right, we see an image of the ammonia converter, the modern ammonia converters, that today combine the catalyst section with the heat exchanger section to achieve decided temperature profile, to strike a balance between higher rates of reaction and constraints posed by the equilibrium consideration. The result is that, in the end, the ammonia productivity increase. Fused iron catalyst is the most studied and widely used catalyst for ammonia synthesis process. This catalyst is derived from three different kinds of iron oxide: leucite, magnetite, and hematite. The catalysts are produced in the same way today. Exact ratio of starting materials are mixed together and fused at around 1600 degrees centigrade. The main difference are additional promoter, type of promoter, and amount of promoter. The general mechanism for ammonia synthesis that come from experimental activities is the Langmuir-Eisenwald mechanism. The mechanism proceeds via the absorption of dinitrogen onto the catalyst surface. This is followed by dissociation of absorbed nitrogen atoms, which is the rate determining step. Direct dissociative absorption of hydrogen two hydrogen atoms proceed, followed the stepwise addition of hydrogen atoms to the nitrogen to sequentially form nitrogen-hydrogen species until to form ammonia, And finally, we have a desorption of ammonia product. Supported ruthenium catalysts are the second most common ammonia synthesis catalyst and the only other to be used industrially for ammonia synthesis. The discovery and optimization of ruthenium-based catalysts led to a new industrial process for the production of ammonia in which it's possible to produce ammonia at lower temperature and lower pressure respect the process that use iron-based catalysts. Ruthenium is most active respect the iron-based catalyst, but from the other side, ruthenium is more expensive and is has shorter lifetime than the iron-based catalytic system. Several strategies for the design of new catalysts based on ruthenium have been evaluated in order to increase the activity and the stability of this kind of catalyst, with objective of minimizing the amount of metal in the catalyst, maintaining high the conversion activity. Most ammonia plants rely on the steam reformation of natural gas to produce hydrogen for the synthesis loop. But the steam reforming of methane produces also carbon dioxide. Coal, heavy fuel oil, and naphtha can also be used, but they have higher carbon dioxide emission respect the natural gas. This process is intensive in terms of energy consumption. It's an energy-hungry process, but has also a significant environmental impact. 1.6% of total anthropogenic carbon dioxide emission come from the synthesis of ammonia. And if we look to the hydrogen produced in the steam reforming plant for the synthesis loop, hydrogen accounts for around 19% of the carbon emission in the synthesis of ammonia. Reducing the amount of carbon dioxide produced during the manufacturing process is dependent primarily on the source of hydrogen. In this case, depend on reforming loop. Steam methane reforming emits carbon dioxide in a concentrated form that is well suited for carbon capture and storage. Up to 90% of carbon dioxide could be captured in this process. But this degree of carbon emission reduction is impressive, but for net zero carbon hydrogen production, current projections suggest that this process can only be part of the transition to a zero carbon solution. This reliance on fossil fuels, natural gas principally, for hydrogen production is why many ammonia plants are looking towards green hydrogen alternatives. Green hydrogen produced via water electrolysis using renewables energy source eliminates carbon dioxide emission and offering a more sustainable pathway for ammonia production. The interest in green ammonia produced using green hydrogen is driven by the need to decarbonize the current ammonia production for its existing uses and by the potential of ammonia to serve as economically viable carrier for long-distance transportation of green hydrogen. Distributed grid ammonia plant will offer liquid storage of renewable electricity at ambient pressure, and ammonia can then be safely transported by ship, road, or rail to the user. The image on the right provides a detailed overview of the ammonia value chain from synthesis, storage, and application. and highlight the various end-use application of ammonia. In general, we can say that ammonia economy has the potential for several energy-related markets, including ammonia as transportation fuel, ammonia for heating application, ammonia for electricity generation, and ammonia as a hydrogen feedstock. The design of green ammonia plants seems more simple if compared with the conventional Haber-Bosch process in which the synthesis loop is integrated with a steam reformer. Here we have an electrolyte to produce hydrogen, then the loop for the synthesis of ammonia is similar to the loop used in a conventional plant. But the transition from conventional ammonia to green ammonia presents several challenges. Economic part is important. The capital expenditure for a green ammonia production plant is dominated by the electrolyte cost. Moreover, the energy supply for green hydrogen feedstock is greater than the electricity demand for Haber-Bosch process. Renewable sources of energy such as biomass, solar, wind, or geothermal are characterized by highly distributed production across regions. Distributed production corresponds to the production at small scale. For green ammonia production, the step forward is downsize a large-scale plant and modularization. If we look at these graphics, when we decrease the ammonia production, the energy consumption increases. This is the real situation. So upon scale down, heat losses increase and the energy consumption increase. So milder operating conditions in the synthesis loop are required for effective scale down. New reactor configuration, alternative to traditional packet bed reactors, should be developed to operate at lower temperature, under 500 degrees centigrade, and lower pressure, under 100 bar, respect the conventional catalytic bed. The cost of ammonia production is characterized by several contributions. We have to consider carbon dioxide emission, electricity, cost of natural gas, maintenance, and capex. As natural gas consumption for steam methane reforming is the most energy-intensive step in the traditional ammonia manufacturing process, is it not surprising that ammonia production costs are strongly correlated to natural gas price? As natural gas price increase, the cost of gray ammonia production rises dramatically. Another important cost element that is the cost of carbon dioxide emission, adding around 12% of the cost. For blue ammonia, we have to consider the cost of carbon dioxide transport and storage. But also in this case, when hydrogen is produced from steam reforming of methane, the levelized cost of ammonia increasing the cost of natural gas. The cost of green hydrogen has a direct and substantial effect on the cost of green ammonia. In a fully electrified ammonia production, based on hydrogen produced via water electrolysis, the hydrogen supply cost would be by far the dominant cost item, as shown by this graphic. For example, if we fix the natural gas price at €50 per megawatt hour, the break-even point for green hydrogen supply costs would be around €3 per kilogram. So, in general, we could say that with hydrogen supply costs expected to decrease in the coming years due to technological advancement and scaling of renewable energy, the cost of green ammonia could become competitive with traditional fossil-based ammonia production. This slide shows an integrated carbon capture and utilization system where methanol and synthetic natural gas are produced as potential energy carriers. The green hydrogen can be combined with carbon dioxide to produce synthetic natural gas and methanol that can be used for several applications. In the case of methanol, we have synthetic fuels and additives for transportation of specialty chemicals. Natural gas can be injected in the grid and used for on heating or for filling station. This approach enhances the flexibility and the sustainability of energy system, promoting the use of renewable energy with reducing carbon dioxide emission. Methanol has the potential to serve as significant energy carrier, thanks to its wide range of application across various industries. Methanol is used in sectors such as automotive, maritime, aviation, construction, electronics, pharmaceutical, and plastic, demonstrating its flexibility and adaptability. As shown in the slide before, it can be synthesized from captured carbon dioxide and hydrogen produced from renewable sources, supporting a circular carbon economy. This makes methanol not only an efficient means of storing and transporting energy, but also a key component in reducing greenhouse gas emissions and promoting renewable energy integration across multiple sectors. On the right is shown a comparison of weight and volume needed to deliver 45 megajoule of energy. Due to its properties by volume and weight, methanol requires the least volume and weight, while batteries and hydrogen need significantly more due to their lower volumetric energy density. Methane is the most popular hydrocarbon used as a fuel. It is an important carrier for electricity generation and heat production. In comparison with the hydrogen, has a higher volumetric energy content and most important is much safer. Methane is a clean fuel when compared to other hydrocarbons since it emits less carbon dioxide per unit of heat produced. If green energy and a source of carbon dioxide are at the end, a prime route to sustainability is the production of synthetic natural gas by methanation. Carbon dioxide is captured and the gas can be directly used in our existing gas grid. The gas grid may be the largest energy storage system which is already in place. It is in fact easier and cheaper to use existing infrastructure such as the gas grid to store large quantity of energy. Just think of wintertime in Europe or other periods where without the necessary wind or sunshine. Here, scale and size is important. Liquid organic hydrogen carrier technology is a method for hydrogen transport and storage that involves bonding hydrogen molecules to a stable liquid carrier compound. Hydrogen is produced by electrolysis and through the hydrogenation process can be stored in this carrier that can be transported for the hydrogenation process for the final use, and then the carrier is transported back to the hydrogen source for reuse. There are a lot of organic hydrogen carrier that can be used with different properties for hydrogenation and hydrogenation step, temperature, pressure, amount of hydrogen loaded. Unlike compressed or liquefied hydrogen, the liquid organic hydrogen carrier enables hydrogen to be stored in a liquid at temperature, ambient, and pressure, significantly reducing the infrastructure and energy requirement for handling and transporting heat. The lock storage and transport concept is used to connect regions with large energy generation potential from renewable source and or low electricity demand to regions with high energy demand and or lower energy provision potential. The principal challenges of the liquid organic hydrogen carrier are the energy for hydrogen release, the unpacking or the hydrogenation process, which release hydrogen from the carrier, often requires significant heat or catalytic processing, adding to the cost. Also, carrier handling is important. The carrier must be transported back to the hydrogen source for reuse, adding a logistic step to the process. And finally, there are inherent energy losses in the loading and unloading process, which can impact the overall efficiency. This slide focuses on the comparison of different hydrogen carriers in terms of hydrogen delivery cost. The cost of hydrogen delivery depends on several factors. Depends on the amount of hydrogen transported, on the transport distance. Depends also on packaging. Packaging is used when referring to the form in which hydrogen is being delivered. Packing refers to the compression or liquefaction of hydrogen or its conversion to a chemical carrier, like ammonia, methanol, or synthetic natural gas. Then we have unpacking. Unpacking means reversing the process to have purified hydrogen at the defined pressure and purity at the UC. This chart illustrated the delivery costs for various hydrogen transport methods: compressed hydrogen, liquefied hydrogen, ammonia, methanol, and liquid organic hydrogen carrier in different configurations. Each bar represents the delivery costs in euro per kilogram of hydrogen broken down into components: transport plus storage, packing, unpacking, carrier, and hydrogen losses. The price of electricity is also included with high price and low price. And this is the case of 1 million tons of renewable hydrogen per year delivered to a single industrial customer via a simple transport pathway through dedicated pipelines or shipping routes. And the transport distance considered is 2,500 kilometers. For instance, the methanol option stands out with the highest cost in both configurations, reaching up to about €5 per kilograms of hydrogen in the high-cost scenario, largely driven by the high carrier cost. Compressed hydrogen show the lowest delivery cost in both high and low cost scenario, primarily due to the lower carrier and unpacking cost. In the case of hydrogen delivered by pipeline, costs are mostly related to the infrastructure, pipeline and compressor. But for short distance, up to 3,000 kilometers, as shown in the graph on the left, compressed hydrogen gas appears to be the cheapest option, particularly in the case of pipelines. But for long distance, liquefied hydrogen, liquid organic hydrogen carrier, and ammonia are the option with the lowest cost. Coming back to this graphic, we can see that for liquid organic hydrogen carrier, the unpacking impact much more on the cost respect the other factor. For ammonia, also in this case, the unpacking has an impact. The dehydrogenation process at cost. In case of liquid hydrogen, the packing is important and add cost to the final cost of delivery of hydrogen. So many things should be considered when we compare different hydrogen carriers in terms of delivery costs. And now the conclusion of this presentation that focuses on the potential role of ammonia and other energy carriers for hydrogen storage and transport, challenges and opportunities. We can say that there are several key factors that need to be considered to identify the best hydrogen carrier. Hydrogen carrier production, hydrogen release, recyclability of hydrogen carrier, application size, infrastructure network, policy, geographical position, and transport length. The best hydrogen carrier depend on the application and context. For example, ammonia and liquid organic hydrogen carriers are good options for long distance, large scale application with existing infrastructure, while methanol and synthetic methane provide flexibility and easy of use with existing energy network. Finally, compressed and liquefied hydrogen are useful options for shorter distance where pure hydrogen is needed immediately. In conclusion, I would like to thank everyone for your attention you have demonstrated by following the presentation from the beginning to the conclusion. I hope this presentation has provided valuable insight into the potential and challenges of different hydrogen storage and transport methods